now let's consider the case where the samples are obtained via IID sampling, and it happens that in this case there is at least one positive result, which was this good news here, that you can construct algorithms for which you can ensure that eventually with enough samples you will be able to learn optimally, which means you can recover the best possible function. But the bad news that comes with that is that although you can be universally consistent, there is no guarantee on how fast your error will converge to 0. Okay, and if we look at how to construct a consistent algorithm, there are two cases. So consistency here means that the expectation of the loss expectation under the sampling of the training data. So now our set of data x1, y1 to xn, yn is a random set. So we can take the average loss that we obtain when we train on a data set of size n and compare that to the loss of the best function, and this has to go to 0 when n increases. Okay. So if your input space, your x, is a countable space, then it's easy to see that if you just kind of remember the training set, if you wait long enough, then you will have seen all the x's that are in this countable space, or at least a significant mass, a significant part of it in terms of probability mass, right? So if you just keep storing the instances that you receive and you wait until you have enough of them, then you will be able to, in the limit, converge to the best error, because you will just have to, for given x, make the prediction that is, so for example, for given x, you obtain sometimes this x with a label 1, and sometimes this x with a label 0, and you just have to count how many times you get label 1, how many times you get label 0. If you get more often label 1, then you would predict 1, and if you get more often label 0, you would predict 0. And this happens to be optimal because the loss that you will obtain when you do that will converge exactly to the loss of the best function, which is sometimes called the Bayes classifier. Okay? But the point is, you can achieve this property without making any generalization, because you only can make good predictions at the points that you have seen in your training data and not at the points that you haven't seen so far. Okay? Now in the continuous space, so if now x is, say, the real numbers or some Euclidean space, there is another kind of trick that allows you to be consistent, which is the measurability of the function. In particular, this function here, this Bayes classifier, well, because of the mathematical setting we are in a way, like just for being able to define probabilities on continuous spaces, we have to assume measurability. And it implies, in particular, that this function will be measurable. And measurable means, I mean, I won't give you the definition, but just a flavor of the idea is that, in a way, it's this, the weakest notion of smoothness that you can have. So measurable means that the function has to be regular in some way. And in particular, when a function is measurable, you can approximate it by continuous function arbitrarily well. Which means that even though it seems that you have not put assumptions on what your target function looks like, you have not said it should be continuous or it should be differentiable of such order or so on, still, the very fact that you are talking about probability distribution on a continuous space implies that this target function have this kind of smoothness property, weak smoothness property. So, so again, you can do the same trick. You can somehow store all the training data that you obtain, and when you have to make a prediction, of course, in a continuous space, you will never see twice the same example, or at least if the sampling distribution is continuous. So if you don't see twice the same example, you have to do some kind of generalization. So you have to, on a new sample make a bet on what could be the label for this new sample. And for that, you can just say, well, I can just do as if my target function was continuous. So if I get a new sample, I predict, say, for example, with the nearest, the label of the nearest example in my training set. And when you do that, you kind of smooth out your training set. So you replace your training set by a continuous function that somehow interpolates this training set. And this is enough, okay, provided certain conditions, but this is enough in general to get consistency. So here there is some kind of generalization that is needed to obtain consistency, but at the same time, it's a bit like cheating because we have introduced, even though we did not want to, but we have introduced some notion of smoothness on the target function. So we have restricted the kind of function that we can obtain. Okay, so now these negative results that come along with this IID setting. So the first one is for a finite sample size. So you have a finite set of training data, and you have, I mean, someone tells you I have 100 training data, and what you can do is for any algorithm, you can construct a distribution, or in that, okay, this is a special case where this distribution has to be such that the base error, so the best error you can get is 0, but you can generalize this statement for arbitrary base error. But you can construct such a distribution which ensures that the expected loss of your algorithm will be as close as you want to 1/2, the worst possible error. Okay, so even if you take a consistent algorithm, you can construct a distribution for which this consistent algorithm on a given n number of samples will do arbitrarily bad. And the point here is that this p that you construct depends on the sample size. So it's a weak statement because, yes?
Oh, so the domain of X, does it have to be continuous, or can it be predicting from discrete to discrete?
Well, actually here, I can, in the next slides I will explain, but here the P is constructed, you can prove this result by constructing a P on a finite set with finite output also, because it's binary classification. So finite set is enough to get this kind of result. Now for the other one, which is now a strong result, which says that, so again, given an algorithm, and given a sequence of numbers that go to 0, so an, you can construct a distribution such that the error of your algorithm will not go to 0 faster than this sequence here. So you can take an arbitrarily slow sequence and make construct a distribution such that your algorithm is at least as slow as this sequence.
So the sequence will be constant?
The sequence has to converge to 0. So it can be constant, but then it has to drop at some point. Because of course you can have consistent algorithms, so you have to have this. And to obtain this, so the difference between those two theorems is that the first one you can do it on a finite set. The second one you need a countable set to construct this distribution. And the idea is to construct a problem for which there is no possible generalization. So essentially, if you have not seen an example, you cannot predict what will be the label of this example. Essentially, the function from x to y is more or less random. Or random, it's deterministic, of course, but it's random in the sense that there is no relationship between the x's and the y's. And when you construct such a function, then what happens is that, so as I said, eventually, if you wait long enough, you will have seen all the samples, whether you are in a finite or countable set, but it may take some time. And this time can be, in a finite set, you can make it for a finite sample size as long as you want, in a way. So if you take, if your finite set of inputs is very big, then it will take you a long time to see a large proportion of this input space. And on a countable space, you can arrange such that for each sample size, so for each n, when you sample on average n points, you have seen a certain number of points in your countable space, but the points that you have not seen yet, they have a probability mass at least an. So and on those points you always make a mistake, or it has to be 2an because you would make 50% mistake. So in the end you have this an error rate. Okay. So just a summary of this. So we have seen consistency is easy in the countable case. It doesn't require generalization, at least within this IID framework, of course. When you are in the continuous case, it relies on the hidden fact that the functions are measurable. And the no-free lunch results, they rely on the fact that even though you may see all the data in the end, it may take time for you to see enough of the data. Right? So now the question is, okay, we have these negative results. What kind of positive results can we have? And in particular, if we cannot prove that it's possible to generalize, because we can always construct distribution where generalization is not possible, what can we do? So that's where comes in the picture this what I called yesterday the decomposition of between estimation and approximation error. So these theorems that we have seen, they try to make the difference between the error of your algorithm and the error of the best algorithm as large as possible. But now this term actually contains two contributions. You can rewrite it in this way. The first term is the difference between the loss of your algorithm and the loss of some function in a class. So you introduce some class of function, which in the regret setting I call the reference class. So you want to compare in a way your performance to some class of classifier. So you compare the loss of your algorithm to the best loss in this class, and then the best loss in this class with the best loss overall among all possible functions. Okay? I mean, so far we have not done anything, it's just rewriting. And usually these two parts, these two contributions are called, so this one is called the approximation error. So this is the best you can do within this class G, right? Within this class G, the best loss you can obtain is this. So the best difference between the loss and the optimal loss is this quantity. And this is deterministic in the sense that it does not depend on the sample, on the training data, right? So it's some number that is fixed. Of course, you cannot compute it because you don't know what is G star. And, well, you cannot even compute L in general. Yes?
Sorry, I mean, why the difference should be as much as possible between loss functions?
Why is the difference? No, it's not. It's
the estimation error you say.
Oh, for this one, okay. Yeah, okay. Let me finish. I'll continue. So this approximation error is deterministic. That's the important point, and you cannot compute it because you don't know what is G star, and you, for example, in particular, don't know whether G star is in your class G beforehand. You can assume it is there, but you don't know, and you cannot check that it is there. Okay. Now the estimation error. So I define this as the smallest loss that a function in G, in capital G, can have, right? So this is L of Gn minus the minimum over G of L of G. So if I take the minimum out, then it becomes a maximum because there is a minus sign. So L minus the minimum is the same as the maximum of the difference between L of Gn and L of G, right? So it just comes from the definition of this quantity here. And this is called the estimation error. I like to call it better the maximum regret, because it's a quantity that you can define even if you don't have this IID framework, even if you are not in a statistical framework. And estimation is a term that is usually used in the statistical framework. Okay? And what it tells you is how much does the data mislead you in making you believe that Gn is good, while the good function is G capital G. Okay? And this quantity, of course, depends on the training data that you have. And the point is, you can quantify, like get upper bounds on this quantity, even if you don't make any assumption about your distribution or about your target function. So that's what is interesting when you do this decomposition, is that you get a term that you cannot say anything about, and another term which you can control. So the idea is now, okay, let's forget about this. Let's say we will never be able to say anything about this, apart if we make assumptions. So let's focus on this term here. And we know anyway that the sum of those two terms can be made arbitrarily large because of the North-Friedland theorem. So let's see how small this can be, or how to control this quantity here. Okay, so again, rephrasing. So we want to focus on the estimation error, or the maximum regret. And because somehow the message is that this learning theory will not tell you how to justify your assumptions, but it can tell you only once you have put these assumptions, once you have made these restrictions, whether or not you believe that they are true is another problem, but once you have made them, what can you do to best exploit them? Okay, so now we'll do a little bit of mathematics finally. I will introduce this. Yes?
Just a quick question. Is this stuff similar to this bias variance decomposition?
Yes, yes. You can
yeah.
see it as kind of a generalization of the bias variance decomposition. Sometimes, although it's not always correct, but sometimes people call this the bias and this the variance.
Yeah.
But it's the same spirit. One is deterministic, the other one is random. So there are three main ingredients when you want to obtain an upper bound on this quantity, this maximum regret quantity. One is deviation inequalities, which are basic probability inequalities about how random variables deviate from their expectation. Another one is called fundamental inequalities. So I don't know why it's called like this, but it's a way to relate the quantity we want to bound to something that we know how to bound. So this estimation error can be related to a quantity that can be handled by probability theory, right? And another ingredient of interest, and actually, in my opinion, this is the most important one, is the union bound. So it's how to relate the deviation of a collection of random variables once you know how each random variable behaves. And you'll see in a minute why this is important. Okay? So, as I said, the quantity of interest, this one, is a random quantity. So when you have, so it's a random variable. When you have a random variable, what can you, the kind of mathematical statement you want to make about this random variable is to characterize how it fluctuates, right? So the first thing you can say is you want to compute the expectation of this random variable. So again, here expectation is with respect to the sampling of the training data. So assuming you were to get repeatedly training samples of size n, and you were to compute the average error that you make, then this would be this expectation in the limit. Right? So that's one quantity of interest. But sometimes people prefer to quantify what are called the tail probabilities, or the deviations, which tell you what is the probability that this quantity is larger than some value epsilon. And why is this better? It's because from this you can recover all the properties of your random variable. So this is the distribution function of your random variable. So it completely characterizes it. Another quantity that some people could be interested in is the worst case value of this random variable. So the maximum over all possible training sample of this difference. Okay, this is usually not done in the IID framework. It's done more in the online framework. But it's just to tell you that it's also something that you can get a handle on. Okay, so we will focus mainly on tail probabilities. So this, okay, what is a bit confusing here is that we have two layers of expectation. One layer is with respect to the training sample. So we have the first kind of random variable that we have is the training sample. And then we have another random variable, which is the test data. So, and that's why the loss of a function was defined in this IID setting as the expected value of the loss at a new test point. Okay. But of course, this cannot be computed because we don't know the distribution. We can only approximate it. And usually, a natural way to approximate this quantity is, given your training sample, to compute the average loss on this training sample. Right? So you have the xi, yi. You compute this for I from 1 to n, take the average. And this is called the empirical loss. So the idea will be to relate this quantity to its empirical estimate. And of course, we know, I mean, it's a simple fact that the expected value of this empirical error is equal to the loss. But here, be careful, we'll see in a minute why this is a dangerous statement. This is true when g is a fixed function. So it will no longer be true when g depends on the sample. So when you have, if you put here your classifier, so the function output by your training algorithm, this will no longer be true. Okay, so now I have put here in these two slides a couple of kind of very basic but useful tools or inequalities that come from a basic probability theory. And what I can propose you is to try to think about how you would prove these results. Most of them can be proved quite directly. So if you want, I can let you some, say, 5 minutes to think about it, and then I give you the answer. So just take a pen and paper and try to prove these things. Well, okay, this does not require a proof in a way, this one, but those two and this one. And I recall what we know about probabilities are the axioms, that probability of something is larger than 0. Probability of everything, so each event is a subset of this everything event in a way. This is 1. And the probability of the union of two events is the sum minus the intersection. Okay, maybe it's a bit trivial. So if we look at the first one, of course, from what I've written here, well, usually this is not written like this. So when you write it like this, it's direct to obtain this, combining this and non-negativity. Okay. For this one, so anyone has the proof? So, okay, so implication here is synonymous for inclusion. So it means A is a subset of B. So when A is a subset of B, then B can be decomposed as A plus the complement of A in B. So you can write P of B as P of A plus P of B minus A in a set notation. And because of the non-negativity, again, you get this one. Well, this is just a matter of rewriting things. So usually it's convenient to, when you have a deviation inequality, when you know that the probability that x is larger than some quantity is less than some function of this quantity, it's convenient to see, given a confidence value, so given a threshold delta, how large can be this random variable with okay, so you want to guarantee that there is a large probability that x is less than some quantity, and to obtain this you just invert this function f. Yes. Yeah, sorry. Well, this of course is monotonic, but the upper bound may not be. Okay, this one is, the trick is to use integration by parts. So you write what the expectation is. Expectation is the integral of the value times the probability. So P of x dx, right? And then you do integration by parts. So this is, okay, you assume that x is larger than 0. So this is integration from 0 to infinity of x p of x dx. And so you differentiate this, integrate that, and integration of p of x gives you the distribution function, and when you differentiate x, it gives you 1, so it gives you this quantity. Right? Another set of interesting results. Again, I let you 5 minutes to think about it. Okay, the first one is more or less a definition. There is some subtlety, but for the second one, I can give you a hint. You have to use the simple fact that the probability of an event is equal to the expected value of the indicator function of that event. That's for Markov's inequality. So, convexity, anyone? Okay, so actually it's a bit tricky to actually prove this statement because it requires some additional assumption that I've not put here. This statement would be true naturally for finite spaces, because remember the convexity of a function means that the function is always smaller than okay, so it means that the function looks like this essentially. And if you take 2 points on the graph of this function, you draw the line between those 2 points, then the function being convex means that the function is always smaller than this value. And you can write it as, and that's the definition of convex function, f of alpha x plus 1 minus alpha y is less than alpha f of x plus 1 minus alpha f of y. And this for any alpha between 0 and 1. Okay? And actually, when you see that, you notice that this is already an expectation. This is the expectation of a random variable that would take value x with probability alpha and value y with probability 1 minus alpha. Okay? And by repeating this argument, you can show that the same is true for any number of possible values. So if you have f of sum of pi xi, which would be the expected value of a function of a random variable that takes value xi with probability pi, where the pi sum to 1. By repeating this inequality, you get that this is less than the sum of pi f of xi, which is exactly the same as saying function applied to the expectation is less than the expectation of the function. Now the trick is that for this to be true for arbitrary continuous spaces, you need some notion of continuity of this function. Actually, it's called lower semi-continuity. So the function has to be such that it has to be equal to the maximum of all the functions that are linear and below this function. So if you draw all the lines that are below the function, and at each, oh, sorry, they should not cross. Okay, and at each point, you take the maximum value obtained by any such line, then it has to be equal to the value of the function. So if you have this, then you can extend this to the limit in a way where you have a continuous distribution. But okay, so it's in general most convex function you encounter are lower semi-continuous, so you don't have to worry too much about that. Markov's inequality. So anyone wants to give the ID? So did anyone think of, I mean, find the trick? Nobody? Okay, maybe. Okay, so maybe that was not enough. Or maybe you are too shy. Okay, so as I said, we start from that, and we start the other way around. So we start from the right and go to the left. So so what we write first is that x, because x is larger than 0, when x is larger than t, then x is larger than t times the indicator that x is larger than t. Okay, so it's a bit stupid to write this, but that's how it works. So what? And actually, this is always true, because either x is less than t and the indicator function is equal to 0, and because we know that x is larger than 0, this is true, or x is larger than t and the indicator is equal to 1, so we obtain x larger than t. So I mean, we don't say much by saying this, but this is enough to prove this result, because now we take the expectation of both sides, expectation of x on this side, and the expectation of the indicator is the probability. So we obtain that the expectation of x is larger than t times the probability x larger than t. Okay, and this is nothing but this statement. Now, for the other ones, it's the same idea. You apply actually, so these are Chebyshev and Chernoff are consequences of Markov's inequality, where you take, before applying Markov, you take a certain function inside the probability. So here, what you do is you replace the probability. So let's write it here. So because this quantity is non-negative, you can, I mean, it's easy to see that the probability that this quantity is larger than something is the same as the probability that the square of this quantity is larger than the square of this something. Of course, it would not be true if we don't take the absolute values, and yeah. So there is an equality between those two events because they are, I mean, every time this is true, and every time this is true, this is true. And you can use actually, so the fact that one event is equivalent to the other event implies that the probability are the same, and this is a consequence, if you want, of this one here. So if here the arrow goes into in both directions, then you use both statements and you get the equality, right? So you just take the square, and here, when you apply Markov's inequality, the expected value of this square here is nothing but the variance of the variable x. So that's why you obtain the variance on the right. Okay, and for Chernoff, you do the same trick, but so you start from x larger than t, and you exponentiate both sides of the inequality. And because the exponential is a bijective function, this is true for any variable x. So you get the probability that x larger than t is the same as the probability that the exponential lambda x is larger than exponential lambda t. And you apply Chernoff again, and that's what you get. And since this is true for any lambda, it's also true for the infimum over lambdas. Okay? So this is, I'm not saying that we will use all of this, but just these are inequalities you might encounter everywhere if you play around with probabilities. So it's good to know them. Okay, so now let's come back to our topic. We wanted to, if I come back a few slides, we wanted to relate this quantity, the expected loss, to the empirical loss. So one thing that we will do now is to rewrite this into a form which is a slightly more convenient. I mean, there is no magic here, but it's just that is more convenient to see what it means. So we introduce some kind of meta random variable, which is the pair xi, yi, right? So this pair here, we call it zi. And same thing for xy, we call it z. And in addition to that, we define another set of functions. So remember, we had this set of classifiers, which were functions from x to y. Now we define functions from x times y to the real numbers. Here it would be 0 or 1. That actually correspond to taking the loss. So I should have written the small l here, but now we're kind of restrict ourselves to the binary classification setting. So it's the indicator that g of x is not equal to y. So, okay, so this is the loss obtained by my classifier g. And for each classifier in capital G, I define such an f. And I take the set of all such f's, and I call it capital F. Okay? Now, once I have done this, of course, I can write the loss as the expected value of f computed at x, y, or z, and the empirical loss as the average value of f computed at the data. Right? And okay, it's just a simplification of notation. The expectation of a function sometimes is denoted by p, where p is the distribution of this function. And the empirical expectation is sometimes denoted as Pn times f. And Pn is usually called the empirical distribution. So it's kind of a sum of Dirac's centered at the data. So it's just to avoid having to write this L, X, and Y. Now we just have sum of f of z. Okay, so sum of f of zi here, and expectation of f of z here. And of course, we can go back and forth because, like, for each f in f, there exists a g corresponding to it, and for each g, there is a f corresponding. So once we have done that, if we look at this quantity, so this is nothing but loss minus empirical loss. Okay, so it's a random variable. And if we look at the collection of all random variables that we obtain when we vary the function g in capital G or f in capital F equivalently, then we obtain what is called an empirical process. So what is a process? Is a collection of random variables, and an empirical process is a collection of such random variables for which each random variable has the so-called empirical distribution, which means it's the difference between an expected value and an empirical average. Okay, so that's what we have here. And I mean, again, this does not bring any significant information, but it's just for you to hear this name, empirical process, and that's really what we are after. So there is a whole theory of empirical processes where lots of tools are developed to obtain upper bounds on quantities like this. Okay, so why is this quantity interesting? So now is where these fundamental inequalities come in. But before that, I'll give you some properties of empirical distributions. So again, same thing, loss minus empirical loss is the difference between an empirical average and an expectation. As we said, or as you probably know, there is this property called the law of large numbers that ensures that if you have a random variable that you take the value of this random variable several times, you take the average value, then in the limit, if you do that enough, it will converge to the expected value of the random variable. So this is what is written here. When n goes to infinity, this quantity goes to 0 with probability 1. So not only is the expected value of the empirical loss equal to the true loss, but also when n goes to infinity, the empirical loss converges to the true loss. So now the question is how to quantify how fast this convergence occurs. And there is what is called Hoeffding's inequality, which does exactly that. In the case where the random variables are bounded, which is our case here, because this f function is the loss computed at a certain point, and the loss is either 0 or 1, so it's bounded. So if you have IID variables, and your function is bounded here between a and b, but actually 0, 1 here is enough, then for all epsilon, the probability that this quantity is large, or larger than epsilon, is exponentially small. Okay? So and this is the quantification of these large line numbers. It tells you that this convergence happens actually quite fast. But how fast does it happen? For this, we need to massage a bit this inequality. So we use this inversion trick that I mentioned before. So what we say is, let's call the right-hand side of the inequality, let's call it delta. Okay? And what we want is to say, okay, let's look, for example, at delta equals 5%. So we want to know how large can the deviation be for 95% of the cases. Right? So what we do is we say the right-hand side is delta, and we extract, we invert this function, so we express epsilon as a function of delta, and it gives you this quantity here. And now we write it like this, with probability at least 1 minus delta, so with large probability, the deviation will be smaller than this quantity here. And okay, so this is 1 in our case, so we can forget about this term. So what is important is to see this term here, which is the square root of something which depends on the level of confidence that we fixed. But okay, assuming delta is always 5%, then you get some value here. So essentially, it's square root of something divided by n, some constant divided by n. So when n increases, this goes to 0 as 1 over square root of n. Okay? And this is a property that you will encounter everywhere. As soon as you have collection of values and you take averages, you always have such a behavior. Or at least when the values are the random variables are bounded. Yes?
Use a similar technique if you do a regression, because there the loss would not be bounded.
Okay, yes. For regression, you have two situations. Either you assume the loss is bounded. For example, you assume that your y's are bounded beforehand. So maybe you know some bound on the values. In that case, you can apply it. Or you have to assume that with high probability they are bounded. So you can say most of the time the y's are less than some value. Or, I mean, you have to get such a result, you have to put some assumption, a priori assumption on how the y will behave. Sometimes you assume that your input space is bounded. And when your input space is bounded, for example, if you use linear function for regression, then the y's will also be bounded. So you have to use some trick, that's true. Okay, so now if we put things together, what we obtain, so with this, for the binary loss function, we obtain that with large probability for a given g, that's what is very important here, we first have to choose the g. So for a given function in our class of function, with high probability, if we keep sampling the training data again and again, we will notice that for most samplings, so for most training sets, the loss is less than the empirical loss plus 1 over square root of n, essentially. Okay? Yeah, so it should be g here. Yes?
Are there random variables that achieve this bound exactly?
Well, we'll see. Essentially, if you take a random variable that has probability plus 1 or minus 1, probability 1/2 to be 0 and 1/2 to be 1, okay, so it's a balanced Bernoulli variable, then it is like this, at least asymptotically. But yeah, we'll see in a minute that there is a refinement of this bound for special cases. But actually, okay, that's the right rate of convergence for most random variables of this type. But for bounded random variables that have, so to achieve, to be maximally deviant for a random variable, you have to concentrate the mass on the extreme of the interval. So if you have a random variable which is between A and B, the worst case is when this random variable takes value A exactly or B exactly. In that case, it's maximally spread out. So which is our case here because it's 0 or 1. Okay, but what can we say about this statement? in a way it's quite limited, because what we obtain is that if we fix a function, so we have a classifier, and after having fixed this classifier, we keep getting training samples, then this will be true for most training samples. But the problem is it's exactly the other way around that happens. We first have the training sample and then construct the classifier. And the set of samples for which this is true for a given function, so you have a function, you look at all training samples for which this inequality is true, it can be different from the set of samples for which this inequality for another f is true. Okay? So if you have a training sample, only some of the function in f will satisfy this. Okay? And this is a problem, because what we are interested in is not an inequality for a function that we know a priori. It's an inequality for a function that depends itself, this fn depends itself on the training sample. And you can go, you can be somehow extreme and say that if I give you a sample, you can always construct a function for which this is very large. This is 1. For example, you just take the function which is 0 on the training data and 1 on the every other point. You will have made this equal to 1. Okay? So there is some kind of contradiction between saying that this, for a fixed function, can be very small and can go to 0, but if you fix the training set and vary the function, it can be very large. So it's not a contradiction, but it shows that what we have done so far is not enough. Another way of writing it, and I think it's okay, the notation does not match with the rest of my slides, so I will do it again here. So assume you can represent your set of function as a line. So here, all the points here correspond to functions in f. Okay? And here you plot the loss, empirical or true loss. So for all these functions, maybe the true loss is like this. So there are functions that have a small true loss and some functions that have a high loss. And this is a fixed quantity, deterministic quantity. Now, when you get a training sample and you compute the empirical loss of all these functions, you get other values. It can fluctuate like this. And this is a random quantity, right? It depends on the sample. So for one sample, you will obtain this. For another sample, you will obtain other values, and so on. So you can imagine this curve fluctuating, and it fluctuates around L, because for each function here, if you fix a function here and you keep monitoring what happens for this function, this is L of f, and ln of f will move around here, but on average will be equal to L of f. That's the first thing. And the range of the fluctuations will be of order 1 over square root of n. And that will be true for each fixed function. So if you look at another point, it's the same. You will have 1 over square root of n if you keep repeating this trick, this sampling. But the point is now, if we look globally at this empirical process, so this set of curves, for a fixed sample, you can always find a point where the difference between the true loss and the empirical loss is quite large. And this might be much larger than 1 over square root of n, especially if this is large. So if you have many functions, then for a given sample, if you look long enough, then you may find a point for which this difference from this and this is large. And in particular, if you have all possible functions, there will be a point where the difference is exactly 1. Okay? So you have to have in mind this picture where if you look here and you fix the point where you look and you vary the training sample, things behave nicely. But if you fix a training sample, so you fix a trajectory here, and you look along this trajectory, things can be very nasty. So how do we control these variations? Okay, so the trick is to first relate the quantity that we are after, which is this maximum regret, to a quantity related to this empirical process. So remember, we want to control the difference between the loss of our classifier and the loss of the best in some set. And to do that, we will introduce the empirical version of these quantities, and we will focus on a specific algorithm. So the algorithm that we will consider here is what is called the empirical risk minimizer. So we now work for the case where Gn is the function that minimizes the empirical error within the class capital G. So that's what is written here. So now Gn is minimizer of ln of G. And once we have this, we can prove this inequality here. Okay, again, you can think of it a few seconds. It's quite easy to prove. It's derived from the definition of the empirical risk minimizer. Okay, so let me write it. We want to compute L of Gn minus L of G capital G. So what we do is we rewrite this by introducing the empirical version of that. So it's L of Gn minus Ln of Gn plus minus L of G underscore G plus Ln of this G, and we add in the end Ln of G n minus what we have added here, which is this, right? We just rewrite things. Now we use the fact that the Gn is the empirical risk minimizer, which implies in particular that the empirical risk is less than this one. So this, because this function is in the same class, is in capital G. This is negative by construction. So then we obtain an inequality here. And both quantities here can be upper bounded by the worst deviation in the class G, which is the supremum. Well, I'm a bit sloppy here with infimum, supremum, and so on. And you can take it as equivalent to mean and max because I'm only working for finite classes. So just mean and max. So this is the maximum deviation between the true loss and empirical loss in this class. Okay, and that's the same thing with expectations. No magic.